Hello, everybody. Sorry about that. Welcome to Vandenberg Air Force Base today. We're coming to you live from California to talk a little bit about the NASA's SMAP mission. That's the Soil Moisture Active Passive mission. Today's NASA Social is being broadcast online for viewers at home, as well as for everyone here in the room. And we're going to hear a little bit from the science team that's behind it. We're going to hear from some of the people who are getting this vehicle ready to launch tomorrow morning at 9:20 a.m. Eastern Time. And we're also going to hear from some of the CubeSats that are riding along on this, taking a ride to space, and some of the experiments that they're going to be doing with the CubeSats. For today's NASA Social, for everyone who's in the room and following along online, please use the hashtag NASA Social in order to follow along on the conversation and be a part of this. If you'd like to ask a question virtually, we're also moderating chat on our Ustream feed at ustream.tv/NASAJPL2. Without any further ado, though, let's jump straight into it and talk a little bit about SMAP. Our first speaker today is the program scientist for SMAP from NASA headquarters, and that's Jared Enton, here to talk a little bit about SMAP.
Hello. Thank you. First off, I just want to say how excited I am and how appreciative I am that everybody came, many from great lengths away. I'm really excited. I'm also really nervous. As somebody said earlier, some of us have been waiting a long, long time for this day to come, in particular tomorrow morning to come. So all that energy we've been building up for a few decades now is coming, and we're all bursting with pride and excitement and looking forward, and we're glad you're here to share it with us, and through you, the rest of the world. I have to say that makes for a very daunting audience for me. I'm used to speaking to either scientists or a very homogeneous group of people. I'm not used to hearing the people, even just the people in the room, your backgrounds is a very diverse set. So unfortunately, a lot of the jokes I usually tell would not go over because somebody's not going to get it. I'll make an 80s reference and half the room will be like, huh? You know, and I'm really not a social media person. You know, pretty much I got left behind as soon as somebody said MySpace. I kind of went, why would you do that? And, you know, I never paid attention to it again. But luckily, in recent days, I've gotten some encouraging words from my family, including my uncle, and he reminded me of something I had done in the past, and that I was lucky enough to give a best man speech at my cousin's wedding, and I did a passable job, apparently. And then I was like, that's what I'm here really to do. It's sort of the best man speech, because you're really not here to see me. You're here to see and learn about SMAP. But I do want to give you, just like a good best man, I'm going to give you sort of not a dirty little secret, but a little insight into SMAP and where it came from. But it also reminded me that in some ways, SMAP is just like a marriage. For those who've read up a little bit, we have two instruments as part of SMAP. One is what we call an active radar, and the other is a passive radiometer. And that's just like a marriage, and for some of us it hits close to home. One of us is a little noisy, but really good focus on the details. And the other one of us is accurate, always right, but maybe forget some details. And if you're like me, I will remind you that you have about 17 shopping days until Valentine's Day. So that's just a little tidbit for me. But SMAP is a wonderful marriage of these two instruments. The other way I was just reminded recently by somebody is that SMAP is also a unique marriage of two different science fields that I know most of the people in the room are smiling because they're into science. But you have two different groups of people. You have geologists and hydrologists who I will jokingly say spend a lot of their time looking like this. Ooh, look at that rock. And then you have meteorologists, people interested in weather, and they spend a lot of their time looking like this. And SMAP is this wonderful blend for those who've been studying these things. It brings those two things together. It brings them sort of scientifically together the way they work. But also it forced us as different groups of scientists to really focus in. My one little insight into SMAP is actually, well, what's SMAP going up for? It's going up to, in part, observe soil moisture, and you'll hear details I'm not usually the details person. That we have great scientists. People were talking about jobs to get. If you can ever get a job like mine where you get to work with smart people, do it. It's great to work with smart people, and we have a bunch following me, and they're going to go over a lot of the details of SMAP and talk about all the great uses for SMAP that have us all excited. But I go back about 15 or 20 years ago when I was looking at soil moisture observations from around the world. And I would talk to geologists and hydrologists, and they'd say, well, I took a soil sample right here, and the soil moisture was 10. And then I went about 2 feet over, and I took it again, and it was 12. And how's that going to work from a satellite that sees this big image? But then I was talking to other people, and we were talking about meteorology. And, well, why is the soil moisture why is it 10? Why was it 12? And to a hydrologist, a lot of it is the soil composition. But to a meteorologist, they say, well, obviously, the rainfall, that's what caused it to be that, or the day's evaporation. And the story or the little analogy I always used to tell people to try to bring these two things together is in addition to thinking about how soil moisture might vary from here to the end of the room, close your eyes and think about your own backyard where you might go out and measure how much water is in the soil. And then think about your neighbor across the street doing the same thing. And then a couple days later, you repeat that. You do it and your neighbor does it. And then a few days later, you guys do it again. And what you guys would see is when it rains on your house, chances are it rains on your neighbor's house as well. When it's sunny in your house, it's sunny on your neighbor's house. So the plants are active and they're using up the water in the soil. So over time, no matter what the value of the soil moisture was here or over there, you guys are going to see sort of two curves. They might perfectly overlap, but in time, there's going to be a correlation. When it rains, you both go higher, and when it hasn't rained in a while and it's been sunny, the soil moisture both goes down. And one of the problems that I was looking at, one of the reasons why I'm really excited about SMAP is think about how far you can go with that. So your neighbor has a pretty strong correlation with you, but what about the person across town? Or what about your friend in another county? Or if you say you live in the middle of the country in Nebraska, what about the person in Iowa? Is their soil moisture going to trend the same way as yours? How far away can you go and still see some relationship? And a lot of that, because if you can't tell, I'm actually a meteorologist by training, not a geologist. I can't really tell one rock from another. But to me, that was the interesting thing, because that is driven a lot by the meteorology. And as you'll hear about, the soil moisture also comes back, and what we refer to as it's not just the value, but also what we refer to as the anomaly in that value, whether it's anomalously wet just after it rains or anomalously dry. And for many of you in this part of the world and the country, you're used to the anomalously dry because you've been in a drought for a while. But it's these things we're looking at, and to sort of bring it all together, what SMAP brings us to is we're not just looking at my backyard and my neighbors and the analogy of the close. We're looking across the whole United States. We're looking across all of North America, all over the world, trying to look at these soil moisture patterns and see how they affect weather regimes, ultimately climate, and we're really looking at the big picture. And that's exciting for some of us who, whether you've been studying soil moisture locally or trying to get observations from across the globe, trying to understand how things work, how they might be similar in other countries to here, or how they're different. And that's some of the exciting aspects of SMAP to look into that. Let's see here. And then I just wanted to quickly touch on, if I could have the Earth right now slide, the other aspect of how SMAP fits into the recent NASA portfolio. This is just some of the recent launches. SMAP is actually the 5th satellite that we're launching in about a year's time frame. It started with GPM, the Global Precipitation Measurement Mission, about a year ago. The Orbiting Carbon Observatory 2 that launched about a half a year ago, and then 2 instruments that are going to be put on the International Space Station. And collectively, these are all looking at different parts of the world and how, as we refer to it, as Earth system science unfolds. And SMAP, just coming back to it, I'll probably break the marriage analogy because I'm going to bring in multiple partners. But SMAP is great because it sits at the core of 3 different cycles. It sits at or not at the core, but in the middle of the water cycle. The rain comes down and it puts water in the soil, but then that's used by plants. But when plants use that water, they become part of the carbon cycle. They take carbon out of the air. And at the same time, people don't always get this. When we talk about energy in the Earth system, we're not talking about gasoline or oil. We're talking about the energy that comes from the sun that heats up the ground and whatnot. And again, soil moisture is part of that. If you've ever sort of noticed, if you have a really wet spring, sometimes you'll have a moderate summer, and that's because a lot of the sun's energy first has to go into heating up that water before it can heat up your ground air temperature. Versus if you have a very dry soil, a lot of that energy goes right into heating it up and making it really hot. But the beauty about SMAP is that, especially for these 2 previous missions, GPM and OCO2, it gives our scientists 2 vantage points into the same problem. One is, for whether it's the water cycle, you're looking at the precipitation, and then you're also looking at the soil moisture, and then for the carbon observatory, you're looking at the carbon dioxide in the atmosphere, and of course, where did it come from? It came from, well, in a lot of cases, it came from plants, and that's where the soil moisture comes in. And this, just these 5, and I don't really have time to talk about the other 2, but just these, of course, are a gateway into the whole NASA portfolio. I suppose the other little thing I should always tell people is people, when I tell people I work for NASA, historically they've always said, so you work on the space shuttle? Or like, no, NASA does Earth science too. We're, in addition to looking way out there, we're really interested in looking right here on the ground, and literally on the ground in SMAP's case, but in the atmosphere. We have other satellites that are looking at the change, talking about the water cycle, change in groundwater. But most importantly, one of the things NASA is most interested in is looking at how all these things come together, not trying to look at one piece in particular just for its, I mean, we're interested in it just for its own sake, but then also how does that link into other things? And as you'll hear about today and hopefully read about online, SMAP is going to be a wonderful part of that. Because it fills in this gap of our knowledge of being able to assess the global soil moisture, which, as I said, is sort of where rain comes in. It's got to go somewhere, and SMAP's going to begin to detect that. And then it's also the beginning of some other processes where water goes on from there. So I think I'll stop now and ask for if there are any questions.
All right. Please remember to raise your hand here, and we'll get you a microphone. And for those of you who are following online for questions, if you go to the Ustream channel, we are moderating chat on there, and that's at ustream.tv/NASAJPL2.
First, thanks for coming out and talking to us about this mission. It's appreciated. Given the current state of the drought in California, what do you anticipate SMAP might be able to tell us about our soil in this state, in addition to what we might already know?
So one of the great things, I mean, in the United States, we're a little bit lucky that we have a lot of, not just, we have some soil moisture observations, but we have a lot of other ancillary measurements. So you can kind of get a good proxy of what the soil moisture is just by looking at precipitation and other things. So I wouldn't necessarily say that SMAP's going to come in and revolutionize what we know about the soil moisture here. At the same time, there are a lot of gaps in what we know. And just driving up here, you could see what I sort of refer to as rangelands, where you have these little grassy areas and then you have a nice green tree. And a lot of these, not just in California, but out west, are, I don't want to say totally unmonitored, but they're not monitored enough. And if you think it's not monitored enough here, it's worse everywhere else. And SMAP's going to look everywhere, and it's going to tell us about the soil moisture in all these places. And through you'll hear a little bit more about it, but through computer models and something we call data assimilation, you're going to begin to get the root zone soil moisture. And I think that's where there's going to be another wave of added information. And that's not just what the satellite sees, which is sort of more the surface soil, but also what we've heard is the root zone, trying to get what the plants are really seeing, what they're feeling. Again, not just the absolute value, but kind of getting a sense of that anomaly. Does the plant think it's really wet or really dry? Where are those cutoffs? And then in terms of practical, how would you react in terms of irrigation scheduling? So not just today, but for the long haul, and maybe even outside my area. But what plants should you think about planting for the long haul? Things like that.
The droughts last year really impacted the crops. I think it was around $30 billion that was lost because of that. Can you talk to us more about how this information will impact farming, specifically our farmers, things that they can do to use this information to help impact crop production?
Right. So I think the best way to say it is the more you know, the better you can plan about just about anything. And what SMAP's really going to do, I mean, SMAP's not going to create water magically to solve all the problems. I wish it could, but it won't. But it's going to give people more information. Just like for those of us who came from the East Coast, you saw 2 days before the blizzard, people knew, and they were able to prepare. And that's what we're trying to give with SMAP and other observations, trying to give the farmers as much information as we can about what's coming now, what's coming down the pike, what can you plan for, and over time, it will be not just the sort of day-to-day or week-to-week, but also the long-term. You know, I go back to one of the biblical stories where, you know, there's the prophet tells the king, well, you're going to have 7 years of feast, but you better plan well because then it's going to be 7 years of famine. So you got to modulate. And that's sort of the theme is we're not going to always give, just SMAP's not perfectly set up to give exact information, but it's going to give that kind of what I would call more general guidance. And then the other thing, more globally, is not only do we care about the plants here, we care about plants in other places. We have a large swath of our agriculture. USDA is looking at how plant productivity is going on other places, and SMAP will give us some insight into how those are doing. And again, that will help people here better plan what they do in ways I don't even know, but more information is better.
And we'll have speakers from USDA and some of the other application users a little bit later today in the program.
I guess I'll ask a data assimilation question in anticipation of that. How do you see the evolving relationship with ESA and others for archive? Like there's the Tiger Water Project in Africa, all the things going on for the FuseNet partners, right, but they're equivalent, and obviously the other CIOS
right,
major partners for the archives working together.
Yeah, I mean that's one kind of data assimilation. Different. I was sort of talking more the mathematical model ones, but I think what the question is referring to is how do you use this data? How do people internationally use this data? And one of the big things we've learned recently, and I think maybe Vanessa or somebody will talk about this, is NASA for years has prided itself on when we launch a satellite, we put the data out there. We want people to use it. It's free. Everybody can use it. When we go to our international partners, sometimes they're surprised. Oh, it's free, you know. But what we've learned from some of our international partners is that's not enough. It's one thing to make the data free and available. It's another thing if they can actually use it. It's you know, even something like soil moisture. I can tell you, I'm not telling you what the value of the water, how much water is in the soil right here, so you could plant a crop right here. I'm kind of giving you an area, and you have to work with end users, whether it's FuseNet or others, on what is this really telling you? How can you use it in a practical way to respond to drought or plan, might there be a drought coming? It's not that easy. I jokingly say, you know, my sister always bugs me because she knows I'm a meteorologist, and she says, I don't really want all these numbers. Do I need to bring an umbrella or not? And that's some of the translation that teams of people both working with NASA and internationally are trying to help people with is how to make that translation from some of the hardcore numbers, but what do they really mean? Most of us know what it means if a car is going 55 miles per hour, but there are other things that we don't always. What does it mean when it hits a wall or something? You know, some of these things that you have to interpret, and that's some of the things NASA and its partners are working on, how to interpret that information and then use it with others. There are going to be times where the SMAP data, don't tell anybody, but SMAP data might be not as good as the GPM data or as good as somebody else's satellite, or for the purpose that somebody really is just worried about a very small field and they have to rely on other satellites. You know, obviously, there's a big commercial industry that might give them information as well. So we're in there with a lot of different groups trying to help them figure out how to use our data, but then also blend it with other pieces of information. One of our other satellites, Landsat 8, has something called the thermal channels on it, and that gives people insight into the plants themselves and how active they are at transpiring and using that water that's in the ground. And that's a very important thing for water managers to know as well.
Wonderful. Well, that's all the time we have for questions with Jared today. He touched on a lot of topics and so on that we are going to be going a little bit deeper on. And so to kick off the next segment here, we've got two wonderful folks from JPL, from the Jet Propulsion Laboratory in Pasadena, California, who are here to tell us a little bit about the spacecraft, the observatory itself, and some of the instruments that are flying on board. So without any further ado, we have Sam Thurman, who's the Deputy Project Manager for the SMAP Observatory. And we also have Wendy Edelstein, who's the SMAP Instrument Manager. And so they're going to talk a little bit about the actual hardware that's going up on the spacecraft.
Well, thank you very much, everyone, and thank you for joining us. I heard a little bit from Stephanie about all that you went through to be here today, which is really impressive. So thank you for going to that effort and coming to share, I think, what for us is a special day on the eve of certainly a mountaintop moment for the project. Now, I realize I look like I just walked off the set of Apollo 13 into this area, so you'll have to forgive me. There were some formal events still approaching the launch, and I was over at the 30th Space Wing Launch Readiness Review this morning. The actual launch authority for our mission is the Air Force Vice Wing Commander. I think someone from 30th Space Wing will be here later today. So obviously they want to hear what's going on before they say, yes, you guys can go and start the countdown and do the other things we need to do to get SMAP into space. Now, for us, the journey to today and being here with you started nearly 7 years ago. So it takes a long time to develop a mission like this. It's a one-of-a-kind mission, as is most of the Earth and space science missions that NASA does. It's also taken hundreds of people, not just at JPL, but many other different companies all over our country, working to make pieces of the vehicle, parts of the software system that'll process data that Jared Enton was talking about a little bit to create the actual data products. In fact, Wendy will tell you about some of the bigger players in the aerospace industry that helped us get here. I think our peak workforce in the fall of 2012 was upwards of 500 people, so it takes a village to fly in space. There aren't 2 or 3 mad scientists with screwdrivers in the high bay doing this. It takes quite a few people with a very broad skill set. So in project management, we really operate at the intersection of all the scientific and technical work that has to be done, laying that out on a timetable and relating all the jobs in such a way that everybody knows what they need to do, they know what people are doing around them, and how all the pieces will come together eventually. And then the most challenging, perhaps the most interesting part of projects sometimes, at least in a management role, is the budget. You have to figure out how much these things may cost. You have to work with that carefully and work with the sponsor, NASA, since this is a publicly funded effort. We do our best to make use of the dollars that are invested in this mission. As I hope you heard from Jared, I think the benefit of that investment is substantial and will go on for quite some time. So at the very least, after the first briefing, I hope you're all appropriately excited about moist soil at this point, and it's important in the Earth's ecosphere. Let me tell you a little bit more about the star of the show, I guess, the machine sitting up on top of the Delta II. Right now, we conveniently have this nice banner with a picture of it. So looking at this from an engineer's perspective, this spacecraft has a few notable features I'll share with you here from the banner. One is, which is not obvious, it's a dual spinner, which means part of it rotates and part of it does not. The upper portion you see here with the gold colored, this is actually thermal blanketing that covers all of the electronics assemblies on the top of the vehicle, the feed horn that works with this antenna. So the radar and radiometer that Jared described can see the ground. They don't actually look at the ground directly, they look up, and this is our mirror, if you're an L-band microwave anyway. Provides a very good view of the ground. We're running a video now, the mapping animation, which shows the way the dual spin works. So the instrument and the big antenna in particular need to rotate so the instrument's footprint moves across the Earth's surface. The big antenna combined with the spinning motion and the offset, the oblique pointing angle of the antenna beam makes for a very large swath across the Earth's surface for each pass of the orbit, but with a very small footprint, so we can have our scientific cake and eat it too. That is, we want high resolution and we want global coverage, and we want frequent revisit. And so the dual spin architecture, if you're an aerospace engineer, is designed to give us all those things on a single spacecraft without having to build multiple copies of them, which would be a more costly way to do such a mission. Other major features, you see a rather large, what we call the solar array. It's a 3-panel array in the middle of this guy. That array generates about 1,500 watts of electric power when it's up in space doing its thing. So if any of you used a hairdryer in your hotel room this morning, a typical hotel hairdryer is about 1,500 watts. So you were blowing the equivalent amount of power on your head before you came over here. The vehicle it's medium size by spacecraft standards. If you stood up next to this, the main portion here with the solar array is a little over 5 feet tall, so it's around the size of a person. The whole assemblage, when it's folded up for launch, weighs just over 2,000 pounds, so perhaps the weight of I think we've used what the Mini Cooper is, sort of a car with a weight that's close to the weight of this thing. I think, as you'll see later on with some of the other speakers, it takes a really big rocket to push something that size up into orbit around the Earth, because the Earth's a big, heavy planet and has a lot of gravity. So that's a little bit about what this thing is, a little of why it works the way it does, and a little bit of who we are and what we had to do to get here after all that you had to do to get here today. So we're looking very much forward to what comes tonight and tomorrow morning, and getting SMAP off the ground and doing its thing. So I'll pause here, I guess, Stephanie, for any questions. Or we'll have so Wendy's gonna go next.
Good morning. I'm Wendy Edelstein. Again, I'm the SMAP instrument manager. Thanks for the introduction, Sam. So my job, I think probably one of the funnest jobs on the whole mission. I'm responsible for the instrument development, the development, the design, the development, the building, the testing, the verification. So a lot goes into my job, and it involves a lot of key pieces. Jared talked about the radar and radiometer. That's the active and passive portion. I know SMAP is sort of a jargony name, but active stands for the radar, and the passive is the radiometer. And when he made the analogy about high accuracy, one's more accurate and one's more careful and precise. So the radar is the precise one, not quite as accurate, and the radiometer provides that accuracy. So those two instruments combined come and create both a high accuracy and high resolution image. And then as Sam talked about the spinning of the antenna, what that provides is another element of accuracy, and that's temporal sampling, where you can have lots of data over a large swath, about 1,000 kilometers. And what that then provides is this global coverage. Every 2 to 3 days, we can get a full map of the Earth and repeat it over and over for the life of the mission. So that's all very exciting. You saw a little bit of the system. The most prominent feature is the antenna, of course. It's a large 6-meter antenna. It's a deployable mesh antenna. What that means is the mesh up here, super lightweight. It's like stocking pantyhose, but gold-plated, so I wouldn't buy them for myself. It'd be too expensive. But it actually provides a very good reflective surface for the frequencies we operate at, which is the L-band regime. So for those who understand frequencies, that's the 1.2 to the 1.4 gigahertz frequency range. So while it looks like it's a transparent antenna for us, it's actually a nice, solid reflective surface for the microwave frequency band. This piece right here is the feed horn, and that is basically your collector. It collects all the energy that comes up from the ground. It's focused in the antenna, and then it goes into the feed, and that's how it then gets into the electronics, where then it goes to the radar and the radiometer electronics, and then it does all the processing that's required to make soil moisture measurements. There's a video, RBA deployment video I wanted to show, because one of the first questions I always get is, how does this thing deploy? So I wanted to show you this video. About 20 days into the mission, you can see that the boom is first deployed, so it takes basically 2 steps. The boom is deployed. It takes about 16 minutes to deploy the boom, and it does it very carefully. So we're speeding it up a little bit on this video, but what happens is it takes a long time. There's a lot of telemetry that's read back. So once the boom is fully deployed, it sits there for a few days, couple days while we look at all our engineering data, make sure everything is doing what it's supposed to do. And then we do the the deployment of the actual reflector. And that's a two-phase process. What's called the bloom, and you'll see that in just a moment. And that's where the antenna blooms passively. There's that word passive again, where we actually cut a wire and it pops. It uses its internal stored energy to pop into place. And that blooms out, you see right there, to about 7 feet or so. And then after that's done, we could do a power deploy, and where a motor actually pulls in the cable and stretches out the structure. And it's been used an analogy, various things. I call it the spinning lasso because we spin it. But this portion of it was one analogy would be a giant golden pop-up tent. You know, when you go to the games, you pop it up, and that's how this structure kind of works. You pull it into place, and the whole structure deploys around it. After that, we then spin up the antenna, and that's about a month into the mission, and then about another month after that is when we start taking science data. I do want to take an opportunity to acknowledge the village that it took to develop this instrument. The radar was developed at JPL by the JPL radar group. The radiometer was provided by the Goddard Space Flight Center, we chose people who are excellent and is experts in what they do. So JPL does a lot of radar. Goddard are experts in the radiometer. The large deployable antenna that you see has been provided by the Northrop Grumman Astro Aerospace Division, not far from here in Carpinteria. And then what makes it spin, the Boeing company, and they do a lot of things well, but one of the many things they do are spinning spacecraft. And so we were able to adapt one of their spin motors to be our spin assembly for our mission. So that's a little bit about how the instrument works, and between me and Sam, I think we could probably take some questions.
Yeah, so is it time for that?
Indeed. It is time for questions about the spacecraft and the instruments. So first question will come over here.
All right. My questions deal with the attitude control of the spacecraft. So you have a spun and a despun.
That's right.
How do the masses of those two sections compare? Is this then a spin-stabilized spacecraft? And if it is, how do you keep the spin axis pointed toward the nadir with each orbit?
Sure. Okay. Very astute. So the mass distribution is about 70-30. The bus is almost 2/3 of the way. The instrument's relatively light, but the angular momentum comparison is different. The angular momentum of the spun side is actually on a par with the lower part. It's not spin stabilized. We have a set of 4 devices. I think you may be in the biz, but we have reaction wheels. It's a big spinning wheel that stores momentum, and by having several of those wheels counter-rotate in the opposite direction that the antenna spins, we can balance out the vehicle so that its net angular momentum is 0. So it's actually 3-axis stabilized, the non-spinning portion, and those wheels use celestial sensors that look at the sun and stars to determine how it's oriented relative to the Earth. And by having knowledge of the orbit which we give it in a data file from the ground, it can figure out which way is down, the nadir direction that he's talking about. And so the wheels operate with small torque motors to adjust the orientation of the vehicle so that it points down and it stays pointing down. So remember, when you're in orbit, the horizon is constantly falling away as you travel over the Earth's surface. So an attitude control engineer would say the bus has to slew constantly at a rate of just under 1/10 of a degree per second in order to maintain that nadir down pointing. So the spinning and the right ground track on the Earth's surface made by the antenna sweep takes place. So I think, did I cover all the bases there that you'd asked? Okay.
They need those momentum wheels. They need constant torque on them with a motor to deal with the stabilizing effect of the spun section.
Some of them use small torque constantly, so that we're doing that slew, that rotation to track the down direction continuously. Others just spin at a constant rate, and because the wheels have very good bearings and are very low friction, it doesn't take much energy to keep them spinning. So those are the ones primarily that balance out the motion of the upper portion that's spinning. And then we have some interesting gadgets called torque rods also on the spacecraft. And what a torque rod makes use of the Earth's magnetic field actually to twist the vehicle in such a way that, since we're constantly torquing those wheels, you don't want them to spin up and spin up and spin up and to the point where they break. That would be bad. So the torque rods subtly operate to balance that out, so we can do what we need to do to make it point, but avoid running the wheels too fast and possibly damaging them. Since they're limited to around, they're pretty quick. They typically run 4,000 or 5,000 RPM, so it's like, you know, running your car up near the red line. Flat out. So that's a little, I'm hardly, sorry if that's tough to follow, but that's the magic the thing does, you know, all in its onboard computer to fly right.
Hi. So, right over here. I had a question about the instruments that you have. So I imagine radar is measuring big metal objects in the sky, and the radiometer measuring different things in the frequencies of radio waves. All those things I don't associate with moisture. So I was wondering how you guys make that connection.
So, I think that when one of the science folks come up, they can probably answer how they convert that to soil moisture probably better than I. But the way I look at it is a radar, it uses an active source of energy. So it uses a microwave radiation. It sends it to the Earth. It reflects it back. That's called the backscatter from the radar. And what it gets back can be associated with essentially the dielectric constant of the Earth. So that is a measurement of how much moisture is in the top layer of soil. So basically the type of signature of the radar return is directly related to how much moisture is in the soil. And now we picked this L-band frequency for a reason. There's lots of different frequencies we can operate at, and the radar would do the same type of work no matter what frequency you picked. However, at L-band, it happens to be a long enough wavelength that you can penetrate. There's no cloud issue. You can penetrate through the foliage and the trees and get right to that top layer, the surface, and it penetrates, up to, depending on how dry the soil is, it could be a meter, it could be a few inch, an inch, just depends on how dry it is. We're measuring the first couple inches of soil or water in the soil basically by how much it gets reflected back from the ground up to the instrument. The radiometer is passive and it just listens. It's a listening system. It basically is measuring heat that's coming back from the surface, and it converts the surface temperature. Again, they have lots of years of ground truth of looking at these types of sensors and correlating what that signature is coming back from the radar and the radiometer, and then correlate that to, okay, that's how much moisture is in the soil. So that's been years and years and decades of understanding how those physical features of the dielectric constant and the temperature feed into the measured amount of soil or water in the soil. Okay?
I had more of a materials question, I guess. I'm sure it's probably silly given how much you guys have reliability tested, but how concerned are you about the mesh being punctured while it's in orbit?
Well, early on, certainly that was one of our big questions. We were concerned that there's what's called micrometeoroids. There's a lot of space debris up there, and yes, there was some concern that you puncture it and what's going to happen with the antenna. Is it going to shrivel and fall apart? And if that happens, does the whole antenna become unstable? So yes, we were very worried early on. So we did lots of testing. We did testing to make sure that if you penetrate it with one piece of debris, it doesn't run. The stockings don't run. These are non-running stockings. So it basically goes right through it. And we did lots of analysis to say, okay, how many holes can we get in the antenna before it actually makes a difference? And we have plenty of margin in our design and to address that.
We actually do a statistical analysis. There's, believe it or not, a catalog that the military maintains of 10 or 20,000 objects down to the size of paint chips. So we can simulate the mission against that catalog as one way of assessing the likelihood something big enough to do damage beyond all the testing and the things Wendy described takes place as well. That's something NASA requires of any satellite mission, not just us.
Yeah, cool. So it sounds like you guys have modeled where and what size it would be and how it would affect the measurements?
Yes, and so we have done all that, and if you look carefully at the data, at the image, you see all these little tie points. So it's tied down in a lot of places, and so we even did studies that if we lost a little region, what does that do to our performance? Because that would be what would maybe happen. We might lose, these are called facets. We might lose one piece of it, but we did a lot of modeling to say, okay, that has, you know, very limited, effect on our overall performance. So that's how we did a lot of modeling and testing to back that up.
I have a question over here. In terms of the long-term data gathering, what is the expected life expectancy of SMAP? How long will it be around?
Sure, I'll take. So if I'll give you a two-part answer. So the manufacturer's warranty, if you will, is a design life of 3 years after we finish what we call commissioning, which is a very careful and thorough checkout of all the vehicle's functions, and, you know, including the instrument involving the science team, you know, some of whom are back here, that get some initial data to verify the instrument's working right in space. One of the hardest things about building these things from an engineering standpoint is being able to predict how good is good enough. So we typically we're conservative in our design practices, so our expectation is we get the vehicle up and working, it will live well past its manufacturer's warranty design lifetime of 3 years. We filled the propellant tank. It only needs about a third of the tank per our simulation analysis to complete the mission, and we filled it up just regardless, in hopes that, you know, after all that so many people have been through to make SMAP happen, that it'll be up there a lot longer than 3 years and being able to generate good data. I mean, if you look at some of the other missions the agency does, like the Cassini orbiter that's been up there, or the Voyager spacecraft, that's often the case. I'll leave you with there was a quote once, I think it was Ferry Porsche, when he was designing racing cars in the 50s for endurance races, and almost all of them broke. Finishing an endurance race was the hardest part about designing cars for them, much less, you know, what you do in the race. So he said that, you know, the ideal racing car functions perfectly till it crosses the finish line, and then it falls apart. But even nobody, since he said that and ever since, has really figured out how to do that. So that's why, you know, we tend to err on the conservative side and over-design these vehicles a little bit to be sure they'll do the required lifetime to meet the minimum science objectives and go well beyond that.
All right, that's all the time that we have today with Sam and Wendy here. Thank you very much.
Thank you. Go SMAP.
I know that there's a lot of questions that are still out there that we haven't had time to get to and so on. If you want to, you are welcome to tweet them at NASA SMAP. If you go and put your question onto Twitter on @NASA SMAP, we have the social media team standing by to field some more of those questions about the spacecraft and things like that in order to get more information out there for everyone who is following along online and here in the room. Up next, we're going to do a deep dive into the science that's happening here and some of the applications for that particular science. So without any further ado, let me introduce the science team lead, Dara Entenkabi.
Hello.
Next up, we have the SMAP science team leader from Goddard, here, Randy Koster. Following that, from the U.S. Department of Agriculture, we have Wade Crow, who leads their science team. And we also have Susan Moran from USDA as well, the Department of Agriculture, from the science team there to talk a little bit about the applications and the end users. So without any further ado, let's do a deep dive into science.
Hello everyone. Let me begin by saying why I thought spending 15 years on this project is such a hot idea. When I was going to grad school, by the way, Randy was a schoolmate at the time. We had a fairly simple understanding of what happens to water in the environment. There was the meteorologists and there were the hydrologists that Jared mentioned. So long as water was in the air, in clouds, raindrops, and so forth, it was in the domain of meteorologists. They tracked it, and once it hit the ground, the moment it hit the ground, then a different group of people in a different building started looking at it from a hydrologist point of view. What happens to that raindrop? Does it infiltrate? Does it run off? Which stream does it go into? And ultimately, what kind of flooding or downstream effect happens. Now, at that time, we started getting access to massive computers, supercomputers at the time. And we started to say, okay, what if we put these things two together? Because in nature, they're not separated. So we started developing models that was both atmosphere and land in terms of where the water is cycling in the environment. And we soon realized that the variable to track in order to keep these two connected is soil moisture. And then we said, okay, we don't have measurements of soil moisture. What do we do? And what you need, actually, is an instrument like this. You need to have probes like this put into the ground, which measure the dielectric constants, the same thing Wendy mentioned. And from that, you can infer soil moisture. But the problem was there were no such instruments widely available to give us what we need in terms of tracking water. So if you go to the first, or the animation. So what we needed was maps like this. This is simulated SMAP data. In order to get that mapping at that resolution with that time update using this instrument, you need about 10 million of these. Not only that, you need to go where that, where all those measurements are. So that seems pretty impractical. So what we did was start modeling soil moisture, and at least it very quickly dawned on me that we have, at least I had no idea what I'm doing. So we needed measurements, global mapping measurements of this variable. We put a team together with the group that's represented here and proposed to NASA to build a mission that can specifically make this particular measurement. And also, we talk about soil moisture linking the water, energy, and carbon cycles. I want to go back to that, how important that is as a scientific insight into how our environment works. Water that's in the soil is the accumulation of precipitation in the past. So it's the water that falls from the sky. And then it evaporates and goes back into the atmosphere, feeds the clouds, and creates rain again. Now, that evaporation is part of the water cycle. Also, just as humans have adapted to maintain our body temperatures by perspiring and cooling our bodies by evaporating water, it takes a lot of energy to evaporate water. When you put a kettle on the range, you have to add heat to vaporize it. So it's also part of the energy cycle. The solar radiation that hits the surface has to get dissipated somehow, and evaporation is both part of the water cycle and the energy cycle. And also, life on Earth, the very basic life on Earth, we all are walking carbon, we eat carbon. The carbon that's in the plants and on land is actually produced, the leaves, the branches, the trees, that carbon is actually carbon dioxide gas that gets assimilated in a process called photosynthesis, where you take water from the roots, bring it up to the leaves, you bring carbon dioxide from the air, you bring sunlight from the solar radiation, and you make the biomass. So that's how the carbon cycle links. So these three cycles that are the fundamental basis of life on Earth are linked through soil moisture. And if it wasn't for soil moisture, these things would go haywire. So we're going to make SMAP measurements like you see, and we're going to put instruments like this around the world to validate our measurements, to make sure we're making the right measurements, we have ground truth. But the thing is that even this instrument is not perfect. It has to be calibrated. So wherever we have this instrument, we also require that once in a while we make true ground truth measurements of soil moisture. So besides this instrument, which has to have needs to be powered and telemetered and all that, we require that wherever we have validation sites, that there be also occasionally another measurement. And to make that measurements, you need a few things. You need an empty tuna can, simple as that, and you make a known volume sample of soil into the can. You take it inside, you weigh it using a device like this, which is a kitchen scale. So you need a tuna can and you need a kitchen scale. You weigh the sample. That's some soil, some moisture. Then you dry it. You can dry it anywhere you want. You can put it on the heating lamp, you can put it in an oven, and you weigh it again. The difference between those two is how much water was in this volume. That's volumetric soil moisture. So this is the gold standard for calibrating our instruments eventually. Now, if it's this simple, why not engage citizen scientists? So we have a program, a collaboration with an organization called globe.gov that make environmental measurements in high schools or K-12. And we have engaged with that program to make this gold standard measurements of soil moisture in high schools, as many partners as we can engage. And they actually can produce, if done consistently and correctly, science quality data for the SMAP mission. And we hope that we really engage the citizen scientists out there in helping the SMAP science returns. So with that, I'll hand over to Randy.
So is this working?
Yeah.
Yeah. Okay. Yeah, my name is Randy Koster, and I'm a hydrologist working at Goddard Space Flight Center. And what really excites me as a scientist is the idea that you can predict variations in the global water cycle. For example, if can you predict a month ahead of time if it's going to be a rainy month in the Midwest U.S., for example? Or can you predict when a drought is going to start or when it's going to end? Those kind of hydrological variations are very important, obviously, to society. If you can predict those, society obviously gets a benefit from that. And it's possible, potentially, to do some prediction if you have the right kind of information. Now, I'm going to preface what I say now with what we all know, and that there's a lot of randomness inherent in the in weather and in seasonal climate and so on. If you're looking for a perfect weather forecast a month from now, you're not going to get it, because there's randomness in the atmosphere, chaos. But if you have information at the start of a forecast, you can effectively, you can think of it like loading a dice. A fair dice, of course, all 6 sides have equal chances of coming up. And if you were a forecaster with no skill at all in producing a forecast, you would just roll a dice and the side would come up and say sunny, and you just say to the people on television, it's going to be sunny tomorrow. But of course, that's going to be a worthless forecast. But if you can load your dice so that more often than not you're correct, then you can actually make forecasts that are useful to people. And what we do in the forecasting world is basically try to load the dice with as much information as we can, make it so that we're right as often as we can be, much more often than if we just chose randomly. So if I go to my first slide, I'm going to show you how it's possible for soil moisture to have an effect on weather forecast. If you start, for example, if you know that your soil is wet on the 15th of June, soil moisture has an intrinsic memory. It remembers. If the soil is especially wet in June, it's going to be especially wet a week after you take that measurement, 2 weeks, even a month or 2 or 3 months. It's going to stay relatively wet compared to usual. And so a wet soil on June 15 means that it's probably going to be a wet soil in July. And that means that in July we're going to have more evaporation than usual. And it's the response of the atmosphere to that additional evaporation that may lead to additional rainfall or cool temperatures or what have you. The atmosphere might respond to that, that difference in the evaporation rate. So because of the memory, the information you have on June 15th can actually have an impact on what you get in July. The next slide, please, gives another example for seasonal streamflow forecasts. Obviously, if rain falls on a dry soil, a lot of it's going to enter the soil. It's kind of like you have a dry towel, you spill water on it, the towel is going to soak it up, and that water is not going to run off into your streams or your reservoirs. But on the other hand, if you have rain falling on a wet soil, well, if you have a very wet towel, you drop water on it, the water is going to run off the towel. It's not going to soak in. In a similar way, a lot of the rain that falls on a wet soil can enter the streams and the reservoirs. And the fact that the soil moisture has some memory, you know that it's a very wet soil, say at the beginning of the snowmelt season, and you know that that soil moisture is also going to be wet into the snowmelt season in 2 or 3 months into the future. you can say something about how that rain or the snow melt what will happen to it, whether it'll run off or whether it'll go into the soil. So it's that kind of thing. It's the fact that soil moisture has memory, and the fact that the atmosphere or streams or what have you can respond to the soil moisture that you're predicting in the future that gives us the potential for predicting variations in the hydrological cycle. And so I'm going to go on now to our next person, Wade, from USDA.
Thank you, Randy. I'm Wade Crow. I'm a research scientist at the United States Department of Agriculture in the Hydrology and Remote Sensing Laboratory. And I'll be speaking to you briefly about the potential role of SMAP in global agricultural food production monitoring. So basically, how much food do we produce and how do we distribute this food among a growing global population? And if we can start with my first slide, as a lot of you know, the latter part of the 20th century saw really impressive advances in our ability to globally produce food. So this plot just shows year-over-year advances in yield, which is the volume of crop we produce per volume of acre cultivated. And the big picture is a rosy one. From 1960 to 2010, we've seen really impressive advances in our ability to produce crop on a given area of soil. However, the bad news is, and sort of the downside is that we also retain the susceptibility to climate events. And so I've labeled some of these climate events here. And a lot of these climate events have to do with drought. Those are years in which we have inadequate soil water in order to produce enough crops. And that has a depressive impact, a reduction in the amount of yield we produce. And so in the background of all this good news about the global agricultural food system, there's the bad news of these shocks. And in particular, there's evidence that we're becoming more susceptible to the impact of these shocks. And my next slide illustrates an example of that. And this example is the 2008 food crisis. And what this crisis was a period of time between about 2007 to 2008 in which global food prices essentially doubled. So there were a complex set of reasons for this, but one underlying reason was the impact of agricultural drought. And there's a great deal of fear or concern that the next drought could produce a similar social impact. And the impact of this drought and a doubling of price that had profound social, economic, even political impacts where it occurred in the world. So the idea is how to better predict and monitor droughts so that droughts don't turn into food crises. And on my third slide sort of makes the connection to soil moisture. Now, soil moisture is the most direct and the earliest indication of agricultural drought. So drought by definition, agricultural drought by definition, is a lack of soil water resources. So you don't have enough water in the soil for agricultural crops to produce fruit, to produce crops, produce grain. So it's the most direct. So it's the most valuable variable identified associated with agricultural drought. And secondly, it's also the earliest. By the time you see agricultural drought manifest itself in vegetation health, it's often too late. So the first indication we'll get of that drought is occurring will be a low soil moisture anomaly in the soil. And the connection to SMAP is very direct. SMAP will be the best soil moisture sensor ever deployed due to its resolution, its accuracy, its global coverage, and its repeat time. All of these qualities we were talking about earlier make it the ideal global soil moisture signal. So better monitoring will equal better response, will equal reduced economic and human impact of these type of events. And to this end, SMAP is working with the key USDA agencies who monitor global agricultural drought and its impact on food production. And on a personal level, my interest is in seeing what SMAP can tell us about agricultural drought, and then relaying that information to these important USDA agencies who do this important work of monitoring the global food production system and allow us better lead time and better warning about instances in which these food production systems might be in trouble. So thank you, and I'll pass it along to my colleague, Susan Moran.
Thank you. I'm Susan Moran. I'm with the U.S. Department of Agriculture, a research hydrologist working with the Southwest Watershed Research Center in Tucson, Arizona. And I'm also on the SMAP science team. And Dara's given us a pretty good overview of the science value of the mission. And Wade and Randy gave us a couple of examples related to weather forecasting and agriculture. And I'm going to try to give a broad overview of the uses of SMAP. The SMAP scientists have really given an unprecedented effort to bring the users in early in mission planning to help us with mission development. And the reason we did that is because we wanted to make our data the best it could possibly be and easy to access. And in return, we asked the users to give us feedback in how soil moisture and freeze-thaw information could help their applications and their decision making. So to do that, we did something a little different. Could you put up the first slide? We offered the users of SMAP, the potential users of SMAP, simulated data. And so since the launch isn't until tomorrow, we couldn't give them real data, but we said, here's a simulation of what SMAP might look like, soil moisture in January. Can you use that to prepare for getting real SMAP data after launch? So several users stepped forward. We call these users the early adopters. And you see the red dots on this image. That's the location of the people that came forward and said, we would really like to use this simulated data, some calibration data, engineering data to try to prepare for the mission. Goes across the United States, through Europe, down to Australia. And these are applications that are running from Africa all the way to the North Pole. I'm going to give you a few examples so you'll understand the kind of the broad applications that the SMAP mission will facilitate. Across the United States, we have early adopters that are using it for monitoring drought, for predicting floods, weather forecasting, as Randy said, and even predicting the water supply for New York City. In the United Arab Emirates, we have some early adopters there who are looking at the use of soil moisture to predict large regional dust storms that affect the health of millions of people in Saharan Africa and through the Middle East. There's an early adopter in Germany who's using some of the radar data to map sea ice. And they're hoping that the long-wave SMAP data will improve the mapping of sea ice and improve maritime navigation. So you could go to the next slide, please. So you can see that these early adopters really are cover a broad range of organizations. We start in the private sector. There's John Deere Corporation, who's working with us to use soil moisture to predict when to plant crops, when is the earliest date that they can get out into the field to plant crops. There's universities like Texas A&M University, who is looking at the impact of hurricanes on power outages. In other words, a power pole in a wet soil is more likely to fall over than a power pole in a dry soil. We're also working with the United Nations, the World Food Program, and they are predicting floods in Africa to try to help the lives and the livelihood of the rural populations there. Two of the early adopters are from the U.S. Department of Agriculture. Wade mentioned them, the Foreign Agricultural Service, and the National Agricultural Statistical Service. So these early adopters are really the face of the SMAP mission, or the heart of or whatever bodily part that is critical for function is what these early adopters are. So next slide shows some of the actual faces of our early adopters. We have, these happen to be people who contributed to a video that we did on SMAP applications. So if you want to go see that video, it's a 15-minute video of interviews of our early adopters and what they're doing. You can see the website up on the screen at this point. But you've got Susan Frankenstein. She's from the Army Corps of Engineers. She's responsible for providing soldiers with information on how to get supplies from one point to another. She's one of our early adopters. Brian Wardlow, he's with the National Drought Mitigation Center. They produce maps of drought across the United States for farmers, ranchers, city planners. Mike Eck is with NOAA. He does work with weather forecasting, producing the forecasts that we use in our everyday life. And all of the people in this video and on this screen, all these early adopters believe that the launch of the SMAP mission is going to make their jobs easier and help people throughout the United States and actually around the globe. So these early adopters are standing in line, they're ready, they're excited about the launch. We're excited that they're providing us feedback. And in the end, we think that the SMAP products that we're going to be able to provide them are going to make decisions easier and help people around the world. That's it for me. I think we can take questions.
All right, if all the panelists can come back on up here, we're going to have questions for the science panel. So we'll do the first question up here.
Hi. So I'm currently working on a project where we're measuring soil resistivities to map aquifers, and I'm wondering how can, or to what depth can SMAP collect data, and how can SMAP help towns regulate their groundwater supplies?
Okay, SMAP is a mapping mission, so it's out in space because we want global maps. And at the frequencies where we're making measurements, we can only see a few inches top of the soil. So we're really looking at the interface between the surface and the atmosphere. Okay, so that's it's not an in situ measurement like resistivity where you can go deep into the ground. But what it's useful for is for making weather forecasts or seasonal climate projections of what to expect. So it's not a direct measurement of what can go into the aquifer, but the larger context of what's going to happen in terms of recharge to the aquifer.
All right, just a reminder that we are taking questions in the moderated chat room on Ustream. So here is one of those questions.
Okay, we've got quite a few questions coming in here. One is whether you could tie SMAP data into smart irrigation systems to modulate watering. Is that something that might be possible?
Yes, theoretically. You can make a connection between SMAP and irrigation regulation and irrigation efficiency. The spatial resolutions at which SMAP makes observations does pose a bit of a challenge. You can't quite get down to a field scale, which you'd ideally like to. But it can tell you soil moisture, and soil moisture is the input variable that you need for these irrigation regulation systems. So there's definitely a connection to be made there.
Great. And could you also answer what the spatial scale of the data will be? And then I think you kind of just did right now, talking about it's not field level. And people are also wondering, how will the data come back? Is it a continuous data stream, or does it come down in chunks?
So the flagship soil moisture product coming out of SMAP will be a 10-kilometer combined active and passive radiometer product. There will be a 3-kilometer radar-only soil moisture product at a reduced accuracy. And these products will be made available once every 2 to 3 days. So it'll be a continuous stream of data, but new data will become available at that type of rate.
And another question was asking whether SMAP data might help estimate methane release from thawing permafrost. Would that be a possibility?
Actually, very much so. That we neglected to emphasize that. When permafrost thaws, it creates waterlogged regions, and that's what SMAP can measure with its radar. And the bacteria there are in an oxygen-deprived environment, so they actually are what's so-called methanogenic bacteria, so they actually produce a lot of methane. So the thawing of the vast northern regions is one of the key contributions to potential global warming because of the methane gas. And that's what, in fact, we have an early adopter specifically focused on mapping inundation.
A question I had on plans for level 4 type products. I noticed you talked about incorporating other models. I'm wondering if there will be standard, there's the Mod 13 Modus type products, if there are planned to be more integrated high-level products, and what the opportunity for regional detailed models
Yeah, the SMAP Level 4 product will be a blend, basically, of the SMAP measurement with other data, such as rainfall data, wind speed data, and so on, in a data assimilation environment. Basically, it combines the best of the different data types, including the SMAP soil moisture, and with the conservation equations and so on that make up the model. So by doing that, for example, the Level 4 soil moisture product will not just be a 2-inch down thing, it'll actually go all the way down to the root zone. We're using the information at the surface from SMAP in conjunction with other data to derive that other information.
Okay. Hi. I come from Washington State, where last year a major landslide devastated the community of Oso. So a lot of people back home are wondering, can data from NASA SMAP help with prevention and community planning in relation to landslides?
Soil moisture is definitely one of the big factors in the potential or risk for landslides and in the creation of landslides. But landslides occur on very small scales, usually a few meters across. And that's just beyond the sensing capability from space. Again, there's a trade-off. You go to space because you want a global map. And you have to give up on some of the applications which are on very local scale, like precision agriculture, if on a plot scale, or landslides.
Hi. So I work with an organization that works with a large group of students, and you stated that there's an opportunity for students to become more involved with the SMAP project. And could you sort of give us some additional details and what sort of initiatives is NASA sort of thinking so students can become more involved?
The GLOBE organization, it's actually an acronym, stands, I have no idea, I can't remember right now, but globe.gov. If you go there, this is a network of high schools around the world that make environmental measurements. And we have worked with them, globe.gov, to produce a protocol for making soil moisture measurements using the advanced technology I just showed. Okay, so it's, there's documents on how to make the measurements, how to report them back to SMAP, and how to get SMAP data. So it's all on that webpage, and we really encourage teachers and students out there to sort of become citizen scientists and produce what could be science quality data to validate ground truth SMAP measurements.
Thank you.
Hi. My question is regarding the flow of water. As you probably are aware, if water doesn't move, diseases can form, and that can impact certain parts of the world where you see like outbreaks such as cholera or hepatitis. Will SMAP help monitor the flow of water and maybe help those areas prevent those type of diseases?
Yes, we are working with the Center for Disease Control to look at human health and malaria related to soil moisture. So we do have early adopters working in the human health area. In addition to flow, certainly the dust storms and other human health issues are coming up. One thing I did forget to mention when I was speaking is that we have a disc that has the early adopter video and results of the early adopter studies. So, and I think that's available outside. Vanessa Escobar put this together for us, and you're welcome to get a copy, and you can put it in your computer and get that information on all these different applications.
All right, last question here.
So the science behind this mission is really fascinating. I'm curious behind its application to other initiatives. Is it practical or even possible to send a similar spacecraft maybe to Mars to measure any potential moisture beneath the Martian surface?
That question actually came up in the L-30 press briefing. One could possibly use the same type of measurements, L-band measurements, in other environments to look for signature of water, which is the dielectric contrast between what the water substance is. But the SMAP measurement itself is obviously focused on the Earth.
All right, let's thank our science panel here for today to tell a little about that. Just a reminder for folks, I know that we've got a lot more questions that we have time to get here to. So as a result, if you want to, you are welcome to tweet them at NASA SMAP. If you tweet them to at NASA SMAP, the social media team there is standing by in order to try to get to answer some more of those questions. Up next, we're going to move into the launch vehicle and talk about the rocket, where SMAP is going to take a ride to space tomorrow morning at 9:20 a.m. Eastern Time. And so without any further ado, from NASA's Launch Services Program, we have Mick Waltman, who's the Vehicle Systems Engineer. And then we also have from the United States Air Force here, we have Colonel Mark Del Rosario from the 30th Space Wing Operations Commander.
All right, good morning. How are y'all today? So somebody told me we're here for a reason. Anybody know why? Nobody? Come on, somebody yell it out. What are we here for? All right, great. Before we get into the launch vehicle and talk about it, Colonel and I decided we needed to take care of something, so y'all just smile, okay? Great. All right. I'm in trouble for that, aren't I, Tiffany? Okay, no problem. Hold on, Colonel's still working. There we go.
Technology.
Yeah, check him out on Twitter. He's got his own feed. Yeah. But no, we're going to talk a little bit about the launch vehicle. I'm going to let Colonel talk about the U.S. Air Force and what they do. Then I'm going to talk about the Delta rocket and a little bit about the flow. So, Colonel Mark.
Thank you, Mick. Well, first off, I want to say welcome to Vandenberg Air Force Base and to the central coast of California. This is just a beautiful place to launch rockets, and we've been doing this since 1958. Over time, we've had close to about 2,000 space lift and test launches here at Vandenberg, and we're ready to put up the 43rd Delta II out of Vandenberg Air Force Base. So my role, I'm the Operations Group Commander, and I'm the Operations Director for this mission. So I have a role and responsibility to make sure that the instrumentation, the area clearance for sea, air, and actually for space as well, is clear before this Delta II and the satellites that it's going to put up there get released. I'll tell you right now, I'm excited. I've been doing this job for about a year and a half. Have about 14 launches under my belt under that year and a half. But before that, I was a squadron commander here on base, also doing launches, and I have 18 there. So this is going to be my 33rd, if I got the math right, space lift launch. Very excited to do this. And I know you guys are here to really feel that excitement as well and hear the thunder and feel the roar of that rocket as it's going into space. So Mick, I want to hand it over to you so we can get over to some of your stuff too.
So as Colonel said, 43rd Delta II out of Slick 2 here, right? 152nd, I think it's Delta 370 as we're referring to it. 370th out of the Delta family for the SMAP mission. This is the 52nd mission for us at NASA, and we're very excited. Not only do we have the SMAP mission on top, but you're going to hear a little bit later about 4 CubeSats that we're flying in 3 P-pods. It's really exciting for us in the educational initiative that we've got. Let me go to the video real quick, and I'm going to show you some processing that we have of the vehicle. This is the first stage arriving here at 8:36, where you're sitting actually, and we transferred over to the transportation lift trailer that heads out to Slick 2, and then the vehicle is actually transported from this building down to the horizontal processing facility. You see it going in there, that they do some preps on the vehicle and get it ready to go. This is then taken out to the pad where the mobile service tower is in the park position. The first stage is then lifted up into the mobile service tower. By the way, mobile service tower is just a fancy name for saying mobile crane. That's really what it is. We lift up the first stage in, bring it forward, made it to the launch mount. Fairings actually arrive at Slick 2 and get put up into the white room prior to us mating the spacecraft on. Because of the way we do the Delta vehicle, the spacecraft's mated and electrical connects are made, then the fairing is encapsulated there. You see one of the 3 solid rocket motors, the GEM 40s, going on the first stage there. Excuse me. Three motors on this one. It's a 7320 for the SMAP mission. You see the second stage, which is made by Aerojet Rocketdyne, into the mobile service tower and then put on top. Here you see the SMAP spacecraft being mated to the adapter stack, and then it's going to be canned up, bagged and then canned up for transportation to Slick 2. You see the canning operations going on right there. That's to protect the spacecraft as we transport from Astrotech down to the pad. Keep the environment clean and everything for the spacecraft. Transport it down to Slick 2, and we do the same thing again. We lift it up in the mobile service tower into the white room. There you can see it lifting up by the foot into the fixed umbilical tower, by the way. Uncan the spacecraft. You can see it's bagged there and mated to the launch vehicle now. We'll close the doors, get the clean room stabilized before we remove the bag. And this is the last operation where you see the fairings going on, and then we close it out and get ready for launch. And we're ready to go. We've processed the vehicle, done all of our testing, our sim flights, and gotten ready to support a launch for 6:20 tomorrow morning. So we at LSP, this is what we do. We help integrate our spacecraft customer with our launch vehicle customer. We have technical expertise and engineering in-house to do insight and oversight, working with our contractors to make sure that the vehicle's ready to go to support mission success. Along with our Air Force brethren, we get ready for a launch tomorrow morning.
All right. I think we're ready for some questions about the launch vehicle and getting ready for launch. So first question will come from over here.
So we talk pretty fast. You slow the questions down because we got to think about them.
I understand the Delta II is an endangered species, so to speak. How many of those are left in the NASA LSP program, and what are the plans for Slick 2 after the supplies are out?
So on the LSP contract, we actually have 2 more vehicles that are on contract for 2 missions. There is a third Delta II out there that ULA has for some operation, but I don't know what that's assigned to yet. But for NASA, we have 2 more coming up in 2016, 2017. And after that point, we'll have to see what happens with Slick 2 and where we go. But we'll deal with that when we get to there. Right now, we want to get a mission success on SMAP and then JPSS and ISAT. But NASA does have 2 more missions on the Delta II vehicle. It's been a really good workhorse for us in our stable of launch vehicles.
Over here. So the amount of solid rocket boosters that you're using for this mission, does that have to do with the velocity that you have to propel the spacecraft to, or is it the weight of the satellite?
So it has to do a little bit with the weight of the satellite and what's required for thrust to escape Earth's gravity. So in this case, we're flying a 7320 because, as you heard from Dr. Thurman earlier, the spacecraft is about 2,500 pounds. It's kind of like on the very low end of what the Delta II is capable of launching. Our next mission will actually use 9 solids because the spacecraft is a lot heavier. So it comes down to the orbital mechanics and what you need to escape the velocity to get into space.
Hi. Oop, I'm over here. Hello. Just wondering, how did SMAP actually get to Vandenberg?
Poof. No, it actually trucked down from JPL. They put it in a shipping container horizontally. It was very restrained to protect the instruments and the antenna mechanisms. They bagged it, and then the whole container was wrapped in bagging, and then that container was put in another container and then trucked down here to Slick actually Astrotech, and was taken out there and went through the whole cleaning process, receiving and inspection.
So what's the acceleration profile of the launch? At launch, how fast are you accelerating, and what's your peak acceleration?
It's a good question. Let me see if I can throw you off. The total weight of the launch vehicle at liftoff is approximately 330,000 pounds. We have about 560,000 pounds of thrust. So a 2-to-1, almost 2-to-1 ratio, 1.875, I think it is, if somebody runs the numbers there, ratio to thrust. So that's how we escape Slick 2's vehicle. We hit dynamic pressure through max Q, or dynamic speed at max Q. We slow down, and then after max Q, we speed back up. That exact number I can't tell you right off the top of my head, but it is pretty fast, roughly 12 to 13,000 miles an hour.
So from if they haven't covered did they cover the launch profile of this, of the rocket? Well, what's going to happen is this rocket's going to go into space. It's going to light off the solid rocket motors, the 3, as well as the GEMS. So what's going to happen is it's launching and going off. The 3 solid rocket motors that are attached, they're going to end at about 64 seconds, but they're going to stay on the rocket past point to go about 99 seconds into the mission. And really, that's from a public safety standpoint to get out of the area of south of us, where there's a Naval Air Warfare Center, and so they're going to release from there.
Really
so
nice of the Air Force to protect the Navy, right?
Yeah, so that's our job here in terms of operating a range, is to make sure that we're providing public safety for everyone around us.
Yeah, and then as Colonel was saying, you'd head off. You have first stage separation, second stage ignition, fairing separation, and about 56 minutes after launch, we'll separate SMAP. And then a few minutes after SMAP launches, we'll deploy the P-pods or the CubeSats. Another question?
What are the advantages to launching at Vandenberg to polar orbit versus launching at, say, like the proposed Alaskan spaceport at a higher latitude to polar orbit specifically? Thank you.
So again, that has to do with the flight dynamics and what's required for the mission. There are advantages and disadvantages out of both. I don't know if you want to weigh in on that from the Space Command side, but I know from the Vandenberg area, we can head directly south or from here without much interference and get to our polar orbit quicker than if we came out of the Alaskan space, where we would have to make a slight dog leg to get onto the polar trajectory.
Really have nothing more to add to that. It does have to do with a lot of the bend in the leg here in California, as well as up in Kodiak, where you might have to do a little more zigzag.
I'm wondering, downrange, NASA had used to work with, I think, Malindi, Kenya, for telemetry. Are you still working with those folks at that part of the world, or?
There's actually a tracking station, Hartebeestok, that is going to track as it goes on. So we're going to use Air Force Satellite Control Network telemetry stations, as well as Vandenberg telemetry stations. So our mission for safety, it ends at about 447 seconds. So it gets past the gate, is what we call. And then from there, all the telemetry from those remote tracking stations, including Hartebeestok, get funneled back here to Vandenberg. We pump that data over to NASA so they can use that for later launches, as well as ULA, so they can make sure that the flight dynamics and all that information is taken into account for future launches.
And so we still do use downrange assets. Again, it has to do with what is needed for each mission, and we work very closely with our Air Force counterparts to get those assets downrange to support the mission.
So what is the maximum speed of the aircraft as it's going up into the atmosphere? And also, how long is the process to construct the aircraft as well?
So as I answered this gentleman over here, I don't know the number right off the top of my head, but it's around 13,000 miles an hour when we're at our top speed with the GEMS and the RS-27 flying. We do throttle back during max Q to protect the vehicle, and then we come back up to speed after we pass through dynamic pressure. Now, to answer your question on manufacturing, SMAP mission has actually been going on for a couple years, about 2.5 years, to get the SMAP spacecraft ready. We started building the Delta II vehicle about 1.5 years ago in Decatur, Alabama. Actually, ULA builds that in Decatur, Alabama. They actually processed that vehicle and had it ready to go for us last May. So we launched OCO2 in July and then put SMAP, the first stage vehicle, up on stand on August 4th. Does that answer your question?
Okay, yeah, just a quick question about the polar orbit again. Is it more difficult logistically to get something into a polar orbit as opposed to like an equatorial orbit?
My answer would be no. However, there is from an orbital mechanics standpoint, that's one of the things we do at NASA Launch Services Program, is we have an analytical group, flight design, flight analysis group that looks into that for each mission. And there's a lot of work that goes into it, a lot of analysis for each orbit that has to be done. So as far as processing the vehicle that we do, it's very similar to what we do on the East Coast with the Cape Canaveral Air Force Station as we do here at Vandenberg, getting the vehicle on the stand, getting ready to go. And the flight analysis behind that is really the difficult part for equatorial or polar. But I would say it's about the same for each mission.
All right, and with that, that is the end of Q&A about the rocket and the ride to space. I want to thank you all for joining us for talking a little bit about that today. So thank you all.
All right, we got one more thing to do. Thank you, guys.
Thank you.
Thank you. All right, up next, we're going to talk about some of the CubeSats that are riding along tomorrow and taking a ride to space, and some of the experiments that are going to be happening there. With this, we have, from the Jet Propulsion Laboratory, we have David Ryder, who's the Griffix Principal Investigator. We have David Klumpar, who is from Montana State University, and he's the Firebird Principal Investigator. And we have John Bellardo, who is from Cal Poly, and he's the Co-Principal Investigator on his mission.
You're going to start.
Welcome. We're very excited to share with you about CubeSats and about the missions that we're working on and why we really enjoy what we're doing here. I'll start with a really quick couple sentences about CubeSats in case you're not familiar with them. CubeSat is a very well-defined standard. You see a couple examples of them up here. What I'm actually holding in my hand now is a deployer. Right, there's a lot of work and effort and energy that goes into making this deployer and making it safe. Right. The CubeSats need to fit inside this deployer. There's a lid on the top, spring-loaded. This is the Cal Poly Peapod. You can see inside there is, thank you. You can see inside there's a plunger, right? So the satellites get spring-loaded in here. When the door is open, it shoots out like a big jack-in-the-box, right? These deployers, these Peapods, get bolted into the, shall we say, less desirable portions of the rocket where there's room, and they ride up to space, and as you heard, a few minutes after the primary satellite is deployed, the Peapods begin to open, and they will eject the CubeSats. Right, in this case, we have 3 different CubeSats missions going on. Right, 3 missions, 4 CubeSats, 4 satellites. And we're going to talk to you a little bit about the science, the technology that we're demonstrating, and the student involvement that is really facilitated by CubeSats.
Oh. Yeah, hi, Griffix. Griffix is an acronym of acronyms, I think, but I'll tell you what it stands for. It stands for GeoCape ROIC Flight Validation Experiment. GeoCape is a mission to put remote sensing, atmospheric remote sensing instruments in a geostationary orbit, specifically instruments that are made to understand the composition of the Earth's atmosphere and the way it changes with time. The big significance of that is that it lets you look over a big part of the Earth over very short periods of time, over matters of hours. What I've always done up to this point is to put something in a low Earth orbit. A low Earth orbit, it takes you up to, well, sometimes 16, but more typically are 3 or 4 days before you come back and look at the same place again. In a geostationary orbit, you can look at the same place for almost ever. And it's something we haven't done yet, and we're really looking forward to being able to do that. The problem is when we started thinking about GeoCape a few years ago, we realized that we didn't have instruments or, specifically in my case, detector that would allow you to acquire data over a big enough area of the Earth to be able to see a continent over a period of several hours. So the ROIC part is a readout integrated circuit. It's a key component of a detector array. In our case, what's significant is that the ROIC we have developed runs at sort of unprecedented frame rates. The ROIC or detector has 128 by 128 pixels, 16,000. And what makes it unique is that we have been able to put the whole signal chain as well as the analog to digital converter in each pixel of the readout. So that lets you do readouts at very, very fast rates. In fact, it runs at about 8 kilohertz. Now, what we're doing with Griffix is to do a flight demonstration of that. One of the issues is always when you build a new piece of technology, you're never quite sure, you've worried about everything you need to worry about. So it's very important that you go away and can do the right test on it. And there's something about putting it in space that you just can't duplicate on the ground. So Griffix is going to do a flight demonstration of the readout integrated circuit that we've developed for the GeoCape mission. I thought you might like to see what one looks like. This is a copy of what we're going to put into space. And it's a little piece of silicon there in the middle. It's about 1 centimeter by centimeter. And it's got a whole lot of wires connected to it, which are all the silver pins that are, or silver gold pins. At any rate, what we've done is to take one of these and build a camera with a lens and put it into a 3U CubeSat. This is 10 by 10 by 30 centimeters. The camera part is the red part here on the bottom. The outside of this is all covered in the end, is all covered in solar panels, so we can generate the power we need to make it operate. The camera looks out in the bottom, the round circle in the red there. The rest of this is all electronics that make the spacecraft work. There's a radio, there's a command and data handling system, and the avionics, the power system. And the yellow thing sticking out the top is our antenna. Now, this is just a plastic 3D printed model, and I kind of made fun of the guys who put this together because they forgot to put Stanley on the yellow. What we use for antennas are a piece of Stanley tape measure, and it's proven to work very well on CubeSats for a long time. In fact, there's a little video I think we have on file in the back. Do you think you could bring it on? It just shows a picture of the real thing, of a simulation going around. There it is. You see it. So you can see that yellow stick. In fact, so that's Griffix in a nutshell. There's a couple of other things I wanted to say. One is that it's always surprising, even though these are such tiny things, it still takes a lot of people to put them together. And I think about 50 people had their hands on the Griffix that we will launch on Thursday. It was a collaboration primarily between the Jet Propulsion Laboratory and the University of Michigan. University of Michigan built the bus and the avionics, essentially the spacecraft, and we at JPL built the little camera that has the Griffix ROIC in it. And there's a picture of a couple of the students at University of Michigan, just a still picture. If you could flash that up, it would be really nice for us. It's Jamie. And I also want to say, this is a CubeSat which was funded by NASA through the Earth Science Technology Office. And it's a program that didn't used to be around, and we used to have a really hard time getting new and exciting instruments built to do space sciences with. But with the Earth Science Technology Office, or ESTO, it's given us a big leg up on being able to move ahead with new ideas to do new measurements, new and better measurements, and new and exciting measurements. So I'll stop with that and turn it over to John. Let Dave go?
Yeah, I'll go ahead. I'm proud to be here and excited. We're within 20 hours of the launch of our CubeSats. This is not a new experience for us, but every time is a little bit of anxiety. We're launching our 5th and 6th CubeSats from Montana State University. In this particular case, we partnered with the University of New Hampshire, who provided the science payload. So this is a scientific mission. If I could have that graphic that demonstrates or that talks about the mission, I'll just speak to it for a brief moment. National Science Foundation has sponsored this effort with the Montana State and University of New Hampshire. And I guess we're having trouble getting that graphic up, but basically Firebird is an acronym. There it is. It stands for, you can read it, a long acronym that very well describes what the mission is all about. We're interested in a mysterious phenomenon that takes place in the Earth's, deep in the Earth's radiation belts that causes killer electrons to be dumped into the Earth's upper atmosphere. The Van Allen probes deep in the magnetosphere of the Earth are measuring what's happening there in the radiation belts. But the phenomenon that causes these relativistic, almost the speed of light electrons to rain down on the upper atmosphere can only really be measured from the upper atmosphere. So while the Van Allen probes are telling us about the the environment out there in the deep space. The two Firebird CubeSats are in orbit on those field lines to look at the phenomenon that is this mysterious dumping of particles. So in order to do this mission, we have built two CubeSats, and I think there's a picture of those coming up here. They're each called 1.5U. Each one is exactly half the length of Griffix, because we still have to fit two satellites into the same size P-pod. Now we heard SMAP weighs about 2,500 pounds. Each one of these little guys weighs 2 pounds. You can hold one of these, well, you can see, you can hold it in the palm of your hand, yet the functionality of each of these guys has to have the same capabilities that replicate what SMAP has. For example, we have a communication system. You heard about the antennas that are Stanley tape measures. We have solar power to charge the batteries. We have a command computer working inside to encode uplink commands and send the data back down to the Earth. So it's a real challenge for the students to put all that capability into just a 2-pound box that's about half the size of a loaf of Wonder Bread.
Thank you, Dave. Now I'm going to tell you a little bit about the ExoCube mission. This is an NSF-funded mission. The objective is to measure the density of some particles up in the upper atmosphere. The particles are all really small. If you're curious, they have an atomic mass of less than 40. And it's actually important to measure it in place. There hasn't been in-place measurements taken for approximately 30 years. We've been doing a lot of ground-based measurements, and we need measurements from actual devices and sensors up there. The spacecraft itself was built primarily at Cal Poly by students, which one of the things that's really exciting and really wonderful about CubeSats is that the university students get to be involved. Teams of 30, 40 students work for a couple years to build this, and at the end they actually get to see their hard work and effort and dedication pay off to fly in space. That's wonderful. That's something CubeSat has facilitated. The instrument that we're flying, the mass spectrometer, was built by Goddard. And the students get a lot of great experience interfacing with, NASA agencies, interfacing with other private companies, some of which they'll go off and work for when they leave the lab. So it's a great experience for the students. It's very exciting to get the science data back, to have that start coming down a number of weeks after deployment. So it's an exciting time in the lab, and obviously, if you have any more questions about the specific details of ExoCube or the science mission, other than the high-level summary that I've provided, you'd be more than happy to answer them during the Q&A time.
All right, and with that, we are going to move into Q&A. So if you have questions about the CubeSats that are launching, definitely raise your hand. We're going to start over here on the other side.
Hi. By virtue of this polar orbit, will your CubeSats be in continuous sunlight?
That's correct. That in fact we're being placed into a sun-synchronous polar orbit, which means, we're putting we're having these satellites. Let me say it this way: the satellites are being put into a sun-synchronous dawn-dusk orbit. So in fact, we see the sunlight 100% of the time. Until sometime in about March or April, where we finally get some drag coefficients that move us into and allow the satellite orbit to precess a little bit. That creates a challenge because we've got the sun blasting down all the time. Our batteries are getting way too much energy from the solar power. We'd like to expend as much of that energy by running our systems full bore, but that heats the spacecraft up. So we've got to walk a very delicate line in terms of operating these satellites, especially during this first couple months.
Okay, we have another question from our Ustream audience, and they are wondering, the student-built CubeSats, whether that data is for students to use for research or what agencies will actually use that data for research.
I'll start, I guess. Our policy at NASA is all data is public. So Our data is available to you. Now, what's actually very interesting about CubeSats, if you happen to have the right radio at home, you could actually download the data to your computer. You could, they're continuously broadcasting, and it's in an amateur band. In fact, we have an awful lot of amateur radio people who will help us collect the data. And I know in the case of Griffix, we put it on a website at the University of Michigan, and anyone who wants to access it in the whole world can do it. So,
yeah, I'll just point out that in fact, anybody that's interested in accessing more information about all of these 4 CubeSats, the 3 missions, you can go to the website that's maintained at Cal Poly. It's http://www.cubesat.org. And you'll find telemetry information. You'll have links to the details of the other spacecraft by going to cubesat.org.
Hi. The Firebird 3 and 4 satellites, are there 2 of them for redundancy, or do they communicate ad hoc with each other?
Yeah, good question. We need the 2 to actually accomplish the scientific mission. We're after understanding the dynamics and the spatial extent of these relativistic electron microbursts, they're called, that I talked about. In order to, by flying just a single satellite through one of those events, it's like driving through a rainstorm. You don't know whether you just approached the rainstorm and then it quit because you drove out of it, or did it just start and end. But if you had a second car following you on the highway, you could say, hey, it's just started raining here. The other guy says, no, not here yet. Whoop, there it is. So that's what we're trying to do with these 2 satellites.
What effect does solar radiation pressure have on the orbit perturbations of CubeSats as compared to a full-size satellite?
Look, it's essentially the same phenomenon. And in fact, it's that sort of phenomenon which will cause the orbits of our CubeSats to decay slowly over time. But the lifetime in orbit is something on the order of 10 to 12 years. It depends a little bit on the drag coefficient and the exact attitude of each of the CubeSats. So it's actually a long time. So.
Yeah, and the photon pressure is so low that atmospheric drag and other effects are really dominant over photon pressure. I mean, think of the total size of these things, and there's just not much surface to be to feel a force.
Other CubeSat questions? Wait for the microphone here.
All right, I have a question on the amount of funding you needed to make a CubeSat. It seems like a lot more inexpensive than building a full-size satellite.
That is an accurate observation. It's a lot less expensive than building a full-size, full-featured satellite like SMAP would be. There are a couple primary cost drivers to the CubeSats. The first is how detailed a science mission you have, because the more complicated an instrument you need to accomplish your mission, the more it's going to cost. The second thing that drives it is how tightly you need to control the attitude of these CubeSats. Some have absolutely no attitude control. They just tumble in space and do whatever it is they're going to do. That's sufficient for accomplishing the mission. Others need very tight pointing and accuracy, so they can point at a specific spot on Earth for the antenna. They can point at a specific spot in space to take a measurement. And those systems end up driving up the complexity and the cost of the CubeSats as well. I've seen CubeSats that may just beacon that could be, just marginally around 100,000 in development effort, not counting the launch portion of it, and then it just goes up from there depending on the complexity of the system that you're trying to build.
However, I'll add it's the cost of developing a CubeSat is not outside of the reach of practically any of you here in the room or any of you who might be watching online. In fact, NASA is currently running a centennial challenge called the CubeQuest Centennial Challenge. Citizen engineers, citizen scientists who have capabilities can get together and propose to NASA to enter the Centennial Challenge contest by building a satellite taking it through some rigorous testing, and NASA will launch a few of the winners of this competition. So check out CubeQuest, just Google NASA CubeQuest, and you'll find a bunch of information.
And I'd also like to add real quickly about it being out of reach or maybe seemingly out of reach. I know of a number of high schools who are working on building CubeSats, right? So if you're looking at is it really cost prohibitive if you want to start one of these programs? The answer is I actually don't feel it's cost prohibitive. It's a great opportunity, even at the high school level, to get students interested in STEM and involved in science and engineering.
Wonderful. Then we got time for one last question here.
Hi, what was the timeline for building the CubeSats, and how did you get college students to stick to that timeline?
Graphics took just about 3 years, and all the students as well as their professor were really dedicated to getting the job done. So they self-managed themselves and did a great job doing it. So
we started Firebird about 4 years ago, and the 2 satellites that we're launching tomorrow are the 3rd and 4th of our series. We launched the other ones about 14 months ago. So in the last 14 months, we built up the last 2. And the students are all doing this as an extracurricular activity. And the whole goal is to take their classroom learning, what they've learned in their engineering and science classes, put them into an interdisciplinary team where they can work together and understand how to apply that new knowledge that they're getting. We get them in as freshmen sometimes, as sophomores. They come in whenever they like in the program, and we try to keep them for 2, 3, 4, 5 years, even put them into grad school and get them there for 6 or 7 years working on satellites.
From my standpoint, it's hard enough for professionals to stay on schedule. Throwing students at it doesn't actually solve the problem. And the reality is, their schedule slips. I think ExoCube was approximately 3 years in the making. There's lots of dedicated students that spent a lot of time to really pull this together in the end.
What effect is 3D printing going to have on the cost of this stuff in the future?
I want to talk on this. The next satellite that we're launching is a 3D printed CubeSat. So this is this is not a model or a mock-up. This is a spare flight structure. It's been 3D printed with a very special material. Instead of using aluminum and doing subtractive manufacturing by cutting pieces of metal off to form the last object, this is built from scratch in a machine, and you can see there are battery compartments built into it, card cages for holding electronics. We've tested this, it's ready to fly, and we're looking forward to seeing a new revolution in satellite manufacturing come out of these kinds of processes. And I didn't plant the question. Thank you.
What percentage of CubeSat proposals actually make it into orbit?
The NASA program that launches our CubeSats for us, and we're highly grateful for that program, it's a competitive process, and the initial win rate is fairly high. Maybe it's better than 50%. And it's been going on for about 5 years now, and there's an annual call through what's called the CubeSat Launch Initiative. About 115, I think is the number, have been selected, and to date, it takes a few years, right, to develop. So to date, maybe 20 or 25 of those missions have flown so far, and the rest are kind of in development and waiting for their opportunity.
All right, and with that, that's the end of our Q&A on CubeSat. So thank you all very much for answering some questions from the crowd today. And with that, that concludes today's NASA Social broadcast for the SMAP mission. Launch coverage tomorrow morning begins on NASA television starting at 7 a.m. Eastern Time for a 9:20 a.m. launch here from Vandenberg Air Force Base in California. If you're interested in participating in a NASA social program just like the one that's happening right now and everything, we actually do have an open opportunity at this point in time to come visit NASA on Monday as part of the State of NASA. If you're looking for information about that at any of our 10 NASA field centers that are out there, you can get more information at www.nasa.gov/social. Additionally, if you want to get more information about the SMAP mission, you're welcome to visit online at www.nasa.gov/SMAP. And you can follow them on Twitter at NASA SMAP. And they also have a Facebook page that you can look for. So with that, that concludes today's broadcast here from Vandenberg. We look forward to launching tomorrow morning for the SMAP mission and getting back some incredible science data and also providing some launch assistance in order to get some of these CubeSats into space. So go SMAP and go CubeSats. Thank you all.